Hi everyone, new video in the series on a chapter on intermolecular forces. This video we're going to look at and talk about how the types of intermolecular forces that are present between molecules affects those molecules, affects the chemical solubility, physical property and chemical property, and also its melting and boiling point, so physical property there. So let's start off by thinking about solubility. So the intermolecular forces between molecules governs the physical property of solubility. That's just what I just said. Anyway, for one substance to be soluble in another, all the intermolecular forces must be of similar strength. Okay, so we're not just talking about something soluble in water here, we're talking more general. Okay, most of this course, when we're talking about solutions, we are talking about stuff dissolving in water because it's the most common here on Earth. But we have to start general and talk about general. So recall that the substance that forms the minor part of the solution, so by mass and volume, is called the solute. And the substance that forms the majority is called the solvent. So don't forget those terms from last year. So for a solute to dissolve in a solvent, the three possible intermolecular forces, or actually I think I might reword this slide, the three possible interactions between the molecules present must be roughly of equal strength. And we'll go more in depth into that. So the intermolecular forces between two molecules of solvent must be roughly equal to the intermolecular forces between two molecules of solute. And they must also be roughly equal to the intermolecular forces between a molecule of the solvent and the solute. So we're talking about the three possible combinations between these two different types of molecules. Okay, if one of these possible interactions is stronger than the others, we don't get solution because they really want to stick together, and they'll stick together and not commingle with the rest of the mixture. So we get separation. And I always like this party metaphor. If all three interactions are roughly equal, all molecules can mingle at the solution party. Not so good of a metaphor. Well, it's a good metaphor, but a daggy metaphor. Anyway, I'm daggy. So here, down the bottom, we've got I'll draw a box around it, we've got a solution because the intermolecular forces between these two is roughly equal to the intermolecular forces between these two, and it's roughly equal to the intermolecular forces between one of each, the attractions between them. So what you end up with is a solution because they're all attracting each other just as much. There's a little pull towards all of them, all roughly equal, and they can all mix and form a homogeneous mixture, okay? Evenly distributed and random. So on the right here, I've got an example using the same kind of model of an insoluble mixture. Here, you can see that these molecules up the top have a very strong intermolecular attraction between them. Much stronger than the intermolecular attraction between these two pink particles, and the interaction between a pink particle and one of these ones is also very small. So when you put all three of them together, they don't mix evenly because these guys just stick together and they don't want to mix. So these guys all stick together and these ones are just left out. So we do not get a homogeneous mixture because one of these attractions is much stronger than the others. And so that just happens and they all stick together. Alright, let's look at some examples. So, is ammonia soluble in water and why? Okay, so when we're talking about ammonia soluble in water, ammonia is the solute and water is the solvent. Should I write that down? Just a little bit of practice. We're assuming that the water is the majority, and we say this is soluble in that. Okay, so what we need to do is the three possible interactions between these molecules and diagnose for each set which intermolecular forces are there. So we have one option is between ammonia, or what I might do is just do the formulas actually. Ammonia and water. Okay, one molecule of each. And then we need to consider the interaction between ammonia and ammonia. And then we need to consider the third possibility of water to water. And we need to discuss what intermolecular forces exist between these two molecules. Okay, so the skills that we were building earlier, now it will help to draw them. Remember, help if I was on a pen, remember water is bent. It has the two lone pairs, and it is polar in this direction because those two polar bonds are equal, but they're not opposite. There's a net dipole moment in that direction. Now also recall that ammonia is trigonal planar because like water there, it has a tetrahedral basis, but, I forgot to do I'm trying to do two things at once, talk and draw, not working out too well. Dash and wedge. As I was saying, ammonia, trigonal pyramidal. Did I say trigonal planar? Trigonal pyramidal, it's three-dimensional. So it's like a tetrahedral basis, but it's missing its top bond because it's got a lone pair. So it's in 3 dimensions. Each of those bonds is polar, and they are equal, but they're not totally opposite. There's a net upwards dipole there in that direction. Okay, so there's our two molecules. So in the first instance, we're talking about a molecule of ammonia. How is it attracted to a molecule of water? And we've got our intermolecular forces down here as a little guide. I put them there. We can cross out the intramolecular. Why did I put those in there? Okay, let's work our way through them, not in any particular order. We've got two polar molecules, so we've got dipole-dipole interactions there. So we don't have an ion dipole because we don't have an ion. We could have hydrogen bonding. Well, remember, hydrogen bonding is just very, very strong dipole-dipole. Okay, so we have dipole-dipole, so we could have hydrogen bonding. Let's diagnose that. In both of the molecules, there must be a covalent bond between a hydrogen and an oxygen, a hydrogen and a nitrogen, or a hydrogen and a fluorine. And we've got that in both cases here. So we do have hydrogen bonding between ammonia and water. And remember, it's not a covalent bond between them, it's just a very, very strong dipole-dipole. So let's tick H bond up here. An ion-induced dipole, well, we haven't, remember those induction ones go with non-polar molecules. So we haven't got a non-polar. Do we have dispersion forces? Yes, because we have electrons. They can be unevenly distributed when they approach each other. Okay, so here in this first interaction, we've got from strongest H bonding, and we've got, of course, dipole-dipole. They go hand in hand. If you've got H bonding, you must have dipole-dipole. But you may have dipole-dipole, but it might not fit the criteria for hydrogen bonding. And we've got dispersion. Hopefully my writing is not too messy. Not the neatest. Okay, the next interaction. We've got ammonia with ammonia. Okay, I'm going to rub these bottom ones out. And let's scribble all over it again. Ammonia with ammonia. Well, we've got two polar molecules because ammonia is polar. So we've got dipole-dipole. And we need to consider, do we have hydrogen bonding, the really, really strong dipole-dipole? We do, because both molecules have nitrogen to hydrogen covalent bonds in them. So between the two molecules of ammonia, we've got really, really strong dipole-dipole attraction. We haven't got an ion, and we don't have a non-polar molecule, so we don't get this induction happening. And we have the dispersion, London dispersion forces, because they can approach each other and they have electrons. So here, with ammonia to ammonia, we have H bonding as well. We have dipole-dipole. And we have dispersion. Okay, and I put the strongest on the left down to the weakest. Okay, two waters. Let's do an erasing for this part. Okay, we don't have an ion with two waters. Do we have dipole-dipole? Yes, they're two polar molecules. Okay. Do we then have really, really strong dipole-dipole? Well, yes, both molecules have oxygen to hydrogen covalent bonds in them, so they are really, really strong dipole-dipole attractions. We don't have a non-polar molecule, so we don't have the two induction forces, and we have electrons. Okay, so we've got the same. I've jumped up to rubber, so we've got H bond for water to water, dipole or dipole attraction, and dispersion. Okay, so for things to be soluble in other things, all three possible interactions need to be roughly the same strength, or they need to be roughly the same force there. Now, hydrogen bonding is the strongest interaction there, the strongest, well, apart from ion dipole, but it is strong. But you can see that all three have the same forces between them. So here, ammonia is soluble in water, because the intermolecular forces between all molecules are of the same strength. So they'll evenly distribute and form a homogeneous mixture with, I was going to say oxygen, with water and ammonia. So ammonia is soluble in water, and we do use ammonia solutions in water later on when we do acid bases, because ammonia is what we call a weak base, but more on that later. Okay, let's do another example. Is oil soluble in water? Now we're going to take a shortcut because oil is a mixture of molecules, but basically they're really long strands, sometimes branched, of this type of thing, a carbon chain with hydrogens coming off it. So we're just going to use this approximation for oil. It's much longer, but it's got the same structure all the way through. And we've got our water. Okay, so remember, water is polar. Okay, now let's look at the oil in its short form, in its zoomed in form. It just consists of carbon to carbon bonds, which of course will be non-polar because there's no electronegativity difference between carbon and carbon. And the carbon-hydrogen bond is non-polar as well because there's very minimal difference. So an oil molecule is a non-polar because there's no polar bonds in it altogether. So we have no polar bonds in a molecule, therefore the molecule's non-polar. So we've got a polar molecule with water. Okay, our three possible interactions. Okay, we can have oil to oil. How does oil attract oil? How does water attract water? And how does water attract oil? Now, I'm sure from experience you know the answer to this, that oil floats on water. Oil and water don't mix. It's very widely known, but here we're going to see why. So next time someone mentions this in your life, you can bore them with the why. I would find it very interesting. Most people wouldn't. But anyway, that's muggles for you. Okay, three possible interactions. Oil to oil. Okay, non-polar to non-polar. Well, we haven't got ion dipole. We haven't got dipole-dipole, so we don't have hydrogen bonding. We have two non-polar molecules, so we don't have an ion inducing a non-polar, and we don't have a dipole inducing a non-polar, but we have dispersion forces between them. So I didn't leave enough room, did I? Just dispersion forces there. Water to water. Okay, let's erase my scribbles over my guide here, my little handy guide. Water to water, we have dipole-dipole because they're two polars. We don't have ion dipole because we don't have an ion. Do we have hydrogen bonding, that really, really strong dipole-dipole? Well, yes, we do, because both molecules, both waters, will have an oxygen to hydrogen covalent bond. So check. Okay, we haven't got a polar molecule if we're talking about two molecules of water. They do both have electrons though, so they can be unevenly distributed. Oh, I don't want to zoom in, go away. So they can be unevenly distributed and they will have dispersion forces. So, water to water, we have H bond. This is terrible, isn't it? It's all squished up here. Dipole, dipole. Maybe I did need to zoom in. Maybe it was telling me. And dispersion. That's terrible, I'm sorry. Water and oil. Okay, let's erase my scribble on the guide here. Okay, water and oil. We have a nonpolar with a polar, so we don't have an ion dipole. And we don't have dipole-dipole because we've only got one polar, so therefore we don't have hydrogen bonding. Do we have ion-induced dipole? Well, is an ion inducing a nonpolar? Well, no, we haven't got an ion. But let's look at this. A dipole-induced dipole needs a dipole and a nonpolar. We've got a dipole and a nonpolar. So we've got the criteria for the dipole-induced dipole. The water will approach the oil and make it slightly polar by attracting the electrons over to one side. And we have also London dispersions because they both have electrons. Okay, so we have dipole-induced dipole, and we have dispersion. Okay, now let's look at the relative strengths here. Oil to oil dispersion, really weak. Water to water, hydrogen bonding even, very, very strong attraction there. And water to oil, dipole-induced dipole and dispersion, fairly weak as well, on the same kind of order as dispersion. So you can see in this interaction that water and water is really strong. They're going to stick together. The water is just attracted to water, they're all going to stick together, and the oil is just going to be left out of the party. It's not going to form a homogeneous mixture. And that is why oil is insoluble in water. So oil is insoluble in water as water attracts itself much stronger, English words, much more strongly, get the gist, much more strongly than oil to water and oil to oil. So we don't get a homogeneous mixture. Should I write that down? No, homogeneous or homogeneous. I'm probably spelling this wrong. Mixture. Terrible spelling. That's why oil doesn't mix with water and it remains immiscible. Remember that term, where they don't mix together. And oil floats on top of water in a layer too because it doesn't interact with water because water just loves itself so much. And it's also less dense than water. So it floats on top. So that's why oil floats on water and doesn't mix. Because water just loves itself too much. Little strong magnets. Strong little boomerangs. Anyway, example 3. Is sodium chloride soluble in water? Well, here's another one that we know the answer to. But, yes, salt is what muggles call a salt. Sodium chloride is soluble in water. We know this from everyday experience, but let's explain why. Okay, our 3 possible interactions are going to be water to water. Oh, I was doing formulas, wasn't I? Water to water. And our next interaction is sodium chloride to sodium chloride. And our third option is one of each. Water to sodium chloride. Oh, okay. Oh, sorry to sniff in your face there. That's terrible. Okay. First one we've been doing heaps of water to water is dipole-dipole interaction and hydrogen bonding. So we've done that plenty. H bond, dipole-dipole, and of course dispersion. So really strong to the very weak. So overall, very strong attraction between water to water. Now sodium chloride to sodium chloride, oh, that's why I put this up here. I've got ionic bonding between them. Remember, ionic solids form an ongoing lattice. So it would be sodium chloride, sodium chloride. So we have ionic bonding. And we've also got water to sodium chloride here. Now that's ions when you put them in water. So we've got an ion-dipole interaction here. We don't have dipole-dipole because we don't have two polars, so therefore we don't have hydrogen bonding because we don't have two polars. We don't have ion-induced dipole. We have the ion, but we don't have the nonpolar molecule. And we don't have dipole-dipole. There is actually between them, because they all have electrons. Remember, even though sodium loses electrons, it's still got its innermost shell. It just loses its valence electrons, so we still have dispersion in here. Okay, so we have ion dipole plus dispersion. Okay, let's look at the relative strengths here. And here is a bit harder because there's a bit of a range. Well, we get some hints because we know it's actually true. So water to water is very strong dipole-dipole up to hydrogen bonding. Oh, why am I want the eraser. Oops. Okay, so very strong interaction up here, the 10 to 40 there. Ionic bonding is this strong one up here, and ion dipole plus dispersion is going to be somewhere in here. So they're all quite large, but one thing I want to hint at too is when you get, say, the sodium plus, and you get waters being attracted to it with the oxygen end here, you're not just considering the one intermolecular force, because in 3 dimensions you can probably get around 5 or 6 interacting together. And I know this sounds like cheating, but I'm just trying to explain why it does happen. So it's not just the interaction between one ion and one water. Remember, we saw diagrams before, and you get attractions between all of them. So between this ion dipole, we kind of get like essentially 5 or 6 ion dipoles around it. And that brings it up onto the order of the ionic, okay? And so that's why we do get solubility, because we get more than one interaction between these particles. And so when you're getting 5 or 6 times some kind of hundreds, it's bringing it up in the order of ionic. So sodium chloride is soluble in water. Because again, the interactions, because the intermolecular forces between them are all roughly equal. Okay. I've got another example, and then we'll start talking about melting points and boiling points. Might end up being another long video, I'm sorry. I'm never short with these distractions. Okay, carbon tetrachloride soluble in oil, and why? Okay, let's get a structure of carbon tetrachloride. We don't talk about it often, but here's a structure. Oh, I want a bond there, not a chlorine, and a covalent bond there. Here's our structure. Here's our Lewis dot structure. One bond between each, so that each of our halogens here now has its full shell and 3 lone pairs, and its carbon has got its 8 electrons in those 4 covalent bonds. So it's a tetrahedral shape. Oh, what am I doing? I want a carbon in the middle, don't I? What an amateur. I'm doing my wedge to show we've got 3-dimensionality here. So roughly tetrahedral there. Well, it should be, but my drawing's rough. Okay, we do have polar bonds. Our negative end for each of them is out towards the chlorines, because they're the more electronegative of the carbon or the chlorine. Are they equal? Yes, they are equal. Are they opposite? Well, two individually are not equal, opposite, but all four together do end up being opposite, so we get a non-polar molecule. So here we have a case where four polar bonds, and they are equal, and they all add up to be opposite, is the word that I'm looking for. So it's a non-polar molecule, carbon tetrachloride. And remember, we approximated oil with a chain of carbons. And the technical term is saturated with hydrogens. Every possible bond is filled with a hydrogen. We'll get to that later on next year. Okay, so it was another non-polar molecule because there was no polar bonds. The carbon-carbon bond is not polar, and the carbon-hydrogen is not polar, so non-polar molecule because there's no polar bonds. Okay, so the first interaction is carbon tetrachloride to carbon tetrachloride. Our second interaction is a carbon tetrachloride to oil. And our third interaction is an oil to oil. Those three possibilities. Carbon tetrachloride to carbon tetrachloride. Well, we've got two nonpolar molecules. So it must just be dispersion forces. And carbon tetrachloride to oil, two nonpolar molecules. Again, dispersion. Oil to oil, two nonpolar molecules, just dispersion. So here, the three possible interactions, although they're very, very weak, are of the same strength. So therefore, we will get a homogeneous mixture between carbon tetrachloride and oil. So carbon tetrachloride is soluble in water. So carbon tetrachloride is soluble in water as the intermolecular forces are roughly equal in strength, if you want to add that. Okay. So, a Drolo video there on polarity and solubility to help you out. And I'm not going to show you this too, but there's charged and neutral atoms interaction there for us to go through. Click on. So now we're going to talk about melting points and boiling points. How does the intermolecular forces between a pure substance affect its melting point and boiling point? So as you can imagine, and what I'm going to talk about here, what I probably said in the words, is that the stronger those intermolecular forces, the more that's holding these particles together, the harder it is to make them wiggle about each other and eventually pull apart. So we need to think about the particle model of matter, and so remember in a solid, it's a orderly pattern of those molecules in an array very close to each other. And when you add heat to that, you add heat energy, you can change the state into a liquid where the particles are still very close to each other. There's no gaps in between them, but they can freely kind of move around each other. And remember, when that's going from a liquid to a gas, what you're doing is you're putting spaces between those particles and you're also giving them a lot of velocity. Okay? So here you can imagine the stronger the intermolecular force is between these particles, it makes the melting point and boiling point higher. Okay? So strong intermolecular forces, high melting point, high boiling point. Weak intermolecular forces, low melting point, low boiling point. I think that's just what I mentioned here. Okay, so what I did, let's take a look at this diagram. So first up, we've got ionic bonding where there's really, really strong attraction between them. This is why ions or ionic solids have very, very high melting points and boiling points on the order of thousands of degrees Celsius, because this attraction between the positive and negatives is very, very strong. And also, we're still in the intramolecular forces here. Metallic bonding, high melting point and boiling point, because the interactions between the electrons that are free flowing around there and the positive nuclei and inner electrons, it's only the valence electrons that are freely moving, really hold it together, give it very, very strong attractive forces. remember we had it up here, we can see. So the metallic was the 75 to 1000 kilojoules per mole, so quite strong and therefore quite high melting and boiling points. But there is a range, remember. So you get stuff like tungsten, which is, I'm probably going to Google this and I'm going to look like a fool, but maybe 4000 degrees Celsius. I could have just embarrassed myself. All the way down to, well, you've got mercury, that's a liquid at room temperature. I figured it's melting point and boiling point. But then you've got stuff like gallium as well, which is melting point, I think it's in the high 20 degrees Celsius. I think it's about 28, isn't it? You can melt it in your hands. So there's a wide range of melting points for metals, wide range of strengths in those metallic bonding. Okay, and then we've come down to the intermolecular forces, and we get hydrogen bonding, which is one of the strongest there. Remember, we're talking particle to particle, so we're not talking about ion dipoles. We're talking about the strongest same to same. So they kind of have a medium melting point and boiling point, and I've drawn little waters here. There's quite, for intermolecular forces, a strong attraction between them. So water has quite a high melting and boiling point compared to other molecules of the same shape and size, because of those strong forces between them. Look at carbon dioxide, which is roughly the same size, a little bit bigger even, but because it doesn't have those intermolecular forces between them, the strong ones, it's just got dispersion forces. It's a gas. So its boiling point's like, at a guess, probably negative 80 degrees Celsius. Again, don't Google, you make a fool of me. I'm just taking a guess. So water, medium melting point and boiling point. When you've only got dipole and not hydrogen bonding, it goes down again. I didn't think of an example. Can I think of one off the top of my head under pressure while recording? No. Okay, that's embarrassing, but that's okay. And then right down below, when there's only dispersion forces between these, you have very low melting points and boiling points. That is quite a full range though. But when you got small particles, with only dispersion forces between them, very, very low melting and boiling points. Think of stuff like oxygen to oxygen. So the oxygen O2 to O2 only has dispersion forces, and it's a gas at standard temperature and pressure because there's not much attraction between them. And think even lower again, you've got stuff like helium, where it's a single atom. So lower dispersion forces, only single atom, and you get a lower and lower boiling point. So there's the spectrum there. Okay, there's an interactive there that you can play with. It's comparing the boiling points between polar and non-polar substances, and it's a good one to play with. I won't do it in this video though, because I can't do it on my iPad. I'll just do these examples. Okay, which of these two have the higher boiling point and melting point of why? Water or methane? Not too dissimilar from the solubility, we need to diagnose what intermolecular forces exist between these, but we don't need to consider the interactions between each, well, in this example, between water and methane. We just need to talk about water to water and methane to methane, because we're comparing a block of water to a block of methane. So, methane, remember, is this one, CH4, and it is tetrahedral shape, but the carbon-hydrogen bond is nonpolar, so we've got 4 nonpolar bonds here, so we have a nonpolar molecule. Okay, and water, we have, definitely, we talk about it all the time, we've got a highly polar molecule, and yeah, the dipole is in that direction, the dipole moment. Polar molecule. Okay, we need to consider how the strength, or what forces exist between two molecules of methane. Well, it's nonpolar to nonpolar, so we've only got dispersion. So dispersion forces exist between two molecules of methane. Water to water though, okay. 2 polars, so we've got, well, let's start from the bottom, why not? We've got dispersion. we're not talking about any nonpolars. We do have dipole-dipole. So dispersion, dipole-dipole. And let's consider if we've got the conditions to meet hydrogen bonding. Well, we've got two molecules with a covalent bond between an oxygen and a hydrogen. H bonding. I'm trying to be careful with my language because of those misconceptions around hydrogen bonding. And we don't have iron dipole. Okay. Out of these two, methane or water, which has the stronger intermolecular forces? Well, water does because it has a dipole-dipole up to hydrogen bonding. So two water molecules stick together much, much more than two methane molecules. So water has the higher melting point plus boiling point, as it has the stronger intermolecular forces. Okay, so which of these two? Water has the stronger. Methane, remember that's kind of what muggles call natural gas, which comes where we've got a grid of gas going to our houses and stuff, where there's a grid, natural gas grid. That's the methane that we're seeing there, so it's a gas. Yeah, so it has a much lower melting point and boiling point, so at standard temperature and pressure, it's a gas. Whereas water is not, it's a liquid. It sticks together much, much better, much stronger, because it has those hydrogen bonding dipole-dipole interactions. Okay, which of these two have the higher boiling point and melting point, and why? Methane or pentane? Okay, I'm going to have to draw your structures here. We'll get to these later in the course, but I'll draw your structures. We know methane. Okay, so don't worry if you don't know these names yet. We will get to them later on in the course. So there's our molecule of methane. We diagnosed that as nonpolar before. Because it has 4 nonpolar bonds and no polar bonds, it's a nonpolar molecule. Okay, and pentane is just a longer chain of this. 1, 2, 3, 4, 5, like a pentagon. Okay, it's every other bond, if it's not to carbon-carbon, is to a hydrogen. So we can draw it and represent it like this. Okay, but as you're seeing is the whole molecule is either carbon-carbon bonds or carbon-hydrogen bonds. So again, we've just got a much longer nonpolar molecule. Okay, so two molecules of methane are going to interact, and because they're two nonpolar, the only option is dispersion. Okay, and because the two pentane molecules are attracting each other, still two nonpolars, it's still going to be dispersion. But I didn't talk about it earlier, did I? I can't remember. But anyway, I'll yak on about it now. Because why not? I'm sure I did in an earlier video here where I talked about the size of the molecule and the dispersion forces between it. Smaller the molecule, just a little tiny dispersion force. But if you've got a longer nonpolar molecule with a longer nonpolar molecule, you get more of these little kind of like induced dipole moments. So lots of little interactions between them. So pentane, because pentane has more I'm terrible. More dispersion interactions, I'd call it. Interactions between two molecules. And then those between two methane molecules, it has a higher boiling point and melting point. Okay, the intermolecular forces between two pentane molecules is stronger than those between two methanes. Okay, a couple more examples. This is getting to be a long one, isn't it? Which of these has a higher melting point or boiling point? Neon or sodium chloride? Oh, this is an easy one. When we're talking about sodium chloride, we're talking about ionic bonding. Big. When we're talking about neon, what exists between two neon atoms? They're non-polar, and so they're just dispersion. Can't spell dispersion. So, sodium chloride it's much larger melting point plus boiling point because it has ionic bonding between particles. And neon just has dispersion forces between particles, or between these, in this case, between atoms. Okay. Example 4, we've got ethanol and ethane. Okay. You don't know the structure of these, so I'm going to draw them out. Ethane is one longer than methane, so it has the 2 carbons in its backbone. Don't worry, we'll get to this coming soon. And ethanol has something extra on there. Similar in structure, but it's an alcohol, so it has an oxygen-hydrogen coming off it like that, with a lone pair there. Okay, non-polar, because we've only got, sorry, I should say that in words, ethane, I was going to say ethanol. Ethane is non-polar because it only consists of non-polar bonds, so the whole molecule is non-polar. Okay, look at ethanol here on the right. The carbon-carbon bond is not polar. The carbon-hydrogen bond is non-polar. But the carbon-oxygen bond is polar. It's going to be that way. And the oxygen-hydrogen bond is polar. Now, within the molecule, are these two equal? No, well, one's between carbon and oxygen, one's between oxygen and hydrogen. So we have a polar molecule because they are not equal and opposite. So we have a polar molecule. Okay, so 2 non-polar molecules, just going to have dispersion forces between the 2 ethanes. It's going to have a low melting point and boiling point. Okay, we have 2 polar molecules here between ethanol and ethanol. And because, so we've got dipole, so it must have dispersion too. Sorry, I'm a bit over the place. Dispersion because there's electrons. There's also dipole because we have 2 polar molecules. Let's consider if it's so strong in dipole that we call it hydrogen bonding. Okay, in each of the molecules, do we have an oxygen-hydrogen bond? We do in both of them because we're considering 2 identical molecules, so we also have H bonding. So you can see out of the 2 that ethanol has very, very strong intermolecular forces, so it's going to have a higher boiling point and melting point than ethane. So ethanol has a higher melting point plus boiling point than ethane, as it has much stronger, are my words coming out right? Intermolecular forces between its molecules. That sounds good. Oh, I've got another example, and I think, well, it's getting a long one. Anyway, ethanol or ethanoic acid. I think I might leave this one till later in the course. I know I'm being lazy, but that's a bit harder because we can't draw these structures. So I'll leave that one till later. we've got some other voices talking about these forces and how they influence our physical properties. So I've got good old Professor Dave and now I forget his name, from Bozeman. He's really good. Oh, we've also got the organic chemistry tutor. Okay, there's a little bit to read there also in the notes on which element has the lowest melting point and boiling point. And it turns out that it's helium and not hydrogen for various reasons. So you can either pause the video or look at our notes to talk about that. And I'm going to leave it there because the next section is here with a syllabus point all about allotropy. So thanks for paying attention for that long one, and I'll catch you next time.